given the way the number of people in the audience is going, my plan is that in the last lecture, if there's only one person that shows up in addition to Antoine, I will give him my medal. Okay, so this has been, we've worked on this for many years, but it started almost 20 years ago. So it's a different set of people who have worked in this. So I thought I would do it, thank them right away, because very often I forget. So the main character in this is Yuri Vilk. In fact, I would say that all the original ideas in some way came from him. We sort of extended in various directions, computing response functions, attractive Hubbard model, and so on, but he sort of laid out the plan. And then Bum-Soo Kyung and Yang Chen did a lot of work also at the beginning, and lately it has been more Dominique Bergeron, Syed Hassan, so some of you know, because he was here as a postdoc, Baman Davoudi. Steve has worked on the attractive Hubbard model. And I would mention today also some work of Anne-Marie Darry, who is at Marseille. As usual, you can ask a question anytime. So last time we discussed the pseudo gap. It was sort of the first thing that came out from cluster calculations. And I would say there are three broad mechanisms of pseudo gap that I perhaps explained a little bit in the first lecture. So there's a phase with a new phase with broken symmetry. That's one of the explanations. So usually it's a discrete symmetry, and it's assumed that it is broadened by interactions. I'm just setting up the time here. Sorry for this. I should have done before. So the second class of mechanisms is the mud physics that I've spent a lot of time on. And today I'll talk about precursors of long-range order. So if you're in 2 dimensions, Merman-Wagner allows a large fluctuation regime. And even with weak correlations, you can get a pseudo gap. So what is the difference between a pseudo gap that comes from long-range spin fluctuations and one that comes from mud physics? Well, at least we know at half filling how to make the difference between weak and strong correlations, and that's this diagram I showed several times, where if you have enough frustration, you can get rid of the antiferromagnetism, and then you can get the metallic and insulating phase. And if you're on that side of this crossover line, you are in the strong correlation regime, and on this side, you're in the weak correlation regime. So what we have seen last time is that there is a way to make the difference between weak and strong correlations in cluster dynamical mean field theory. If I plot doping as an interaction strength, normally at zero doping, that's the metal insulator transition, and we saw that there is a first order line, surface also, that separates correlated metal from a pseudo gap. And that line, if we look at the corresponding critical point, is directly linked to the MUT, the transition at half filling, the MUT critical point. So it is really, in some ways, these cluster methods make a sharp difference between weak and strong correlations at low temperature. Now, early indications that there's a difference between weak and strong correlations in the pseudo gap came from cluster perturbation theory. So what is cluster perturbation theory? You just take some cluster that's relatively large, and then you include the effect of the other clusters, if you want, that form the infinite lattice through perturbation theory in T over U. And so in these calculations, these are the results that we got for the momentum distribution curve. And these are the experimental results where you see that the probability that electrons are here is much larger than here. So that's a zero frequency as a function of momentum. So the pseudo gap is different from the mud gap. So the mud gap, if you look at the where the states are, you will see that even if you dope, you can still see a region where there is, for all wave vectors, there's a gap. And it's not at zero frequency because you have doped. That's what's left of the mud gap at finite doping. On the other hand, there's a different object, that's the pseudo gap, that is close to omega equals 0, this depression in density of states, and only in regions that are nearly connected by pi-pi. And the pseudo gap is independent of cluster shape and size in these methods, and it's not caused by antiferromagnetic long-range order. It's not so sensitive to T prime, the nearest neighbor hopping, and it scales like hopping. Now, what about the weak correlation pseudo gap in these cluster methods? What we find is that it's mostly a depression in the weight. It depends on system size and shape, and it's located precisely at the intersection of the Fermi surface with the antiferromagnetic Brillouin zone. So that's the calculation, and that's the observation from Armitage et al. So an early indication that the correlations are weaker in the electron dope than in hole dope is simply that you see here U equals to 4. So if you take U equals 6 or something like that or more, then this piece here always disappears in cluster perturbation theory. So it's a very robust statement. There's also the fact that the optical gap is smaller, that this quantity, the mu dn, is smaller in the electron dope. And even in slave boson calculations at U equals 6, this piece disappears. So if you see this, it's an indication that the coupling is not so large.
Sorry.
Yes.
In a whole dot, you mean disappear, but because you have an arc instead of having a...
That's the whole dope.
Yeah, so it doesn't really disappear, it becomes an arc.
In the whole dope, the Luttinger surface is in some ways far enough from this that it's not affected too much. But once you electron dope, then you find that this becomes very close to this boundary, and if U is large, you get rid of it.
Okay. It's only in the electron dope that...
It's only in the electron dope, yes.
In order to have it, you need U to be small.
Yes, exactly. That's the statement. Yes, Antoine?
So here, in the electron dope calculation, U is small enough that you really have some sort of hotspots physics.
Yes.
You have some
Yes.
narrow region
Yes.
as a crossing with antiferromagnetic zone where the positive particle is suppressed.
Yes.
So do you remember in this calculation what is the typical value of the correlation length that you have?
Okay, that I will show you.
Okay.
So that U is different is not so surprising. After all, the crystal structure is quite different. Here, the copper, this is old dope, and the copper is the red sphere. And you see that it's there's an oxygen octahedron around it, whereas in the electron dope, there's no apical oxygen. Well, just by looking at the structure, it's hard to guess that U would be smaller. But if you add you know that you're adding electrons, so screening will be better in some ways. But so I showed you one proof. The other one are these calculations of LDA plus DMFT. So these are the calculations from the Rutgers group, and they evaluated sort of an effective kinetic energy by using the F-sum rule, integrated up to some cutoff. And the argument is not so simple, and I'm not sure I understand all the details, but the statement is that if you are in this Slater or weakly correlated limit, as you enter the antiferromagnet, this kinetic energy should go down. Whereas if you're in a MUT system, like in whole dope LSCO, that's the other way around. So this is this effective sum rule as a function of temperature for 10% doping. So and you see that the trend is different here. When you enter the antiferromagnet, it's going up. Now we know that the theoretical difficulties we're facing is low dimensions, where quantum and thermal fluctuations are important, large residual interactions, and that by now we would like to be as quantitative as possible. So even in the weak correlation regime, I've shown this before, if you do just RPA calculation, you see that you're okay with conservation laws, but you don't satisfy the Merman-Wagner theorem that tells you that antiferromagnetism should show up only at 0 temperature in 2 dimensions because of thermal fluctuations. And also you don't satisfy the Pauli principle. In this Moria approach, you need to do this type of factorization in a Hubbard-Satonovich transformation, and you have 2 adjustable parameters, the coupling constant here and U effective. So you lose the link with the Hubbard model, and also you don't satisfy the Pauli principle. The same in the fluctuation exchange approximation, which is like Eliashberg theory, but here you don't have Migdal theorem, and you're dropping the vertex correction that should really be there. And as a consequence, you don't have a pseudo gap, and you don't have the Pauli principle. Renormalization group does better. On the other end, in RG, to get the self-energy, you need to go to 2 loop. You need to do it functionally, so it's really a big calculation. And also, you lose control of the calculation as soon as you get close to a large antiferromagnetic correlation length, or as soon as you get close to a phase transition. So if you have a theory with a small parameter, how should we proceed? First, I would say you need to identify important physical principles and laws to constrain non-perturbative approximation scheme. So from weak coupling, it's the kinetic energy that wins. In strong coupling, it's the potential energy. But apart from that, and physical principles like conservation law, Pauli principle, you don't know very much. So if you want something analytical, you should benchmark it against exact numerical results. In this case, it means quantum Monte Carlo calculations. It would be nice also to check that weak and strong correlation approaches agree in the intermediate range. And finally, you want to compare with experiment. So in this talk, I will do just the reverse. So I will compare with experiment. And I want you to keep in mind that agreement does not mean that we have a good solution to the Hubbard model. We could have, the Hubbard model could be inappropriate for that compound, and we could be doing a bad enough solution that it fits the compound. But after that, I will show you the benchmarks, because it is a little bit more of the kitchen, if you're on the cookbook thing. And just before the break, I'll tell you how it works, what are the physical principles that are important. And after the break, then that's a chance for you to leave if you're not interested in more analytic considerations. So let's start by a theory compared with experiment. And let's start with the pseudo gap. So I remind you that that's the whole dope cuprates, and that the electron dope cuprates. In electron dope cuprates, the T star is much closer to an antiferromagnetic phase boundary than in than the whole dope. Here, it sort of makes sense to think that antiferromagnetic fluctuations have something to do, but in whole dope, it's less clear. So in all what I would show you now, almost all, we will have the Hubbard model. We'll use these parameters. So hopping T is 1. T prime, which is this second neighbor hopping, is this value, and T double prime is this. And that's just what comes out of band structure theory. Well, I mean, there are uncertainties, but that's the right order. Then we take for hopping 250 millivolts. So the calculations will be at the equivalent of 200 Kelvin. And what I will show you is like the upper quadrant of the Brillouin zone. So the non-interacting Fermi surface is this line. We fill it with electrons, and that corresponds to an electron dope situation. So the physics in the end will be simple. It's just that these hotspots correspond to scattering out of antiferromagnetic fluctuations. So these are the results of experiment. So this is the RPS spectrum for different wave vectors. So we move along the Fermi surface, and we have 15% doping. So these are energy distribution curves. So, for example, this peak here is, so the Fermi level is here at omega equals 0. This axis is frequency. So what you this peak here corresponds to this place. So there's a peak because there's weight near the Fermi energy. Here you are at pi over 2, and again there's weight because there's a peak near the Fermi energy. Now, what are the results of the calculations? So this peak here is what we see in the calculation. This peak there is what we see here. And the clear difference is that we don't have these long tails here. I don't know why. I mean, they could come from multiple scattering, or it could be really a defect of the calculation, but we don't have these long tails. On the other hand, if you look here where we have weight that is missing, you see that the weight is pushed away from omega equals 0. It's the same thing that you see here. And you see even the experimentalists have identified some peak here, which corresponds to the end of this arrow. And there's another peak closer to the Fermi energy, which is this little bump here. Now, we need to be in, U is our only fitting parameter. We knew it cannot be too big, but it cannot be too small also. At this temperature, if U is too small, you see you lose the hotspot because the antiferromagnetic correlation length is not long enough. We will see later why it's important. If U is too large, that's what I told you earlier, you see you remove completely the weight at the Fermi level, so this would disappear. And in cluster perturbation theory, that's what happens also. So in the end, these are the Fermi surface plots. And you can see this as a defect of this approach, I don't know. But if you move closer to half filling, you have to increase U a little bit if you want to do a detailed fit such as the one I showed. The difference is not huge, and after all, it's just an effective model. And it's normal that the screening is better if the doping is larger. Here it's 15% doping, here it's 10% doping. But still in the work of the Rutgers group, where they looked at LDA plus DMFT, they were able to fit without changing the value of U like we did here. Nevertheless, the U was small. Yes, Indranil?
So you showed two bumps in the theory calculations. How does it fit with the experiments?
Well, these are the two bumps here, this and this. And I mean that there's this and this. I don't know if you see, there's a small, it's not a big bump, but there's one here and one there. And these are these two little bumps, and they are observed right here. No. I just mean, I think that the first bump, I mean, the experimentalists identified it. If they had not done it for me, I would have never done it. But I think this just goes up because it's some weight that's cut off by the Fermi function. And then the peak, because of antiferromagnetic fluctuation, the peak is that would have been there is sort of spread over some range, so it goes down elsewhere. I don't think there's anything very deep there.
Isn't it somewhat surprising that a small change in U value can produce such big?
Well, it depends how close you, I mean, it all depends on whether you're on this side of that line or that side of that line. You see, we did the calculation at 200 Kelvin. So, here is the temperature at which, in these calculations, that the solid line, in which the pseudo gap appears. This is the optical pseudo gap, the dashed line, and this is where the antiferromagnetic correlation become infinite. So that's where the antiferromagnetic phase appears. In these calculations, the pseudo gap is about 10 kBT star. Yes?
I'm confused. I thought your TPSC approach respects non-invariant.
Yes. So this is the experimental result for the antiferromagnet. So these, the open symbols are all with experiments. And clearly the antiferromagnetic long-range order will come from third dimension. Okay, so now the prediction is that this line appears when the antiferromagnetic correlation length becomes larger than the thermal de Broglie wavelength. So that will answer your question of how large the length, correlation length is. I will explain in a few minutes. So first, what is the thermal de Broglie wavelength? Well, that's what you have in the physics textbook on statistical mechanics. There's a sort of a spread in energy that comes from kBT. That spread comes from a spread in wave vector, which is much smaller than K Fermi, obviously. And the gradient of epsilon is h bar V Fermi, so I put it there. And then I just convert the spread in wave vector into a length, and that's the thermal wavelength. And in these units that theorists love, where kb is equal to 1, h bar equal to 1, and even 2 pi is equal to 1, this is what you want to remember, that C scales like V Fermi over temperature. So is this observed experimentally? Well, the group of Greven here, when he was at Stanford, did detailed measurements of the antiferromagnetic correlation length as a function of temperature in NCCO, which is electron dope cuprate. And whatever the details here, I just plot their results here. So this is temperature, this is doping, and the color is the size of the correlation length. This region here is where the correlation length antiferromagnetic becomes 400, so they decide that's ordered. Okay? And then where the pseudo gap opens up in the optical measurement is where these open dots are. Now you see in this region, you need a correlation length of 2 to have a pseudo gap. But if you go down here in temperature, you need something that's at least 10 times bigger if you follow the color code. So where does it occur? It occurs, the pseudo gap here, I will show analytically in the second half, occurs when the antiferromagnetic correlation length is proportional to the thermal de Broglie wavelength. That's what they found in this experiment, but let's say it scales like the thermal de Broglie wavelength. But where things stop to work is here near optimal doping. You see, near optimal doping, the correlation length goes blue again. In fact, if you draw it, it's like this. So it's as if when you get close to the superconducting phase boundary, there's an interference between superconductivity and antiferromagnetism, which is not taken into account in this theory. That's one possible explanation. The other one is that there's something wrong with the experiment, but I wouldn't dare to do this, say this. So the physics is simple to understand. This is temperature as a function of doping. And in this one-band Hubbard model, you would have a mean field transition somewhere here along this line. Instead, since the theory respects the Merman-Wagner theorem, we have a crossover where the correlation length becomes large. So above the mean field, if you plot energy versus K, and then the single particle spectral weight, you will just see a peak at the Fermi energy. At low temperature, so at 0 temperature, you have an antiferromagnet. So now you have opened up a gap, and at the Fermi wave vector, which is right there, you will see 2 peaks. Now what, if I heat up, then I don't lose the correlation length is still large. So you get this 2 peak structure, and that's the origin of the pseudo gap at the hotspots. That's just another calculation that we did with Subir. In this experiment, they showed that Z, the dynamical exponent, was equal to 1. And if you do the calculation in the regime that seems to be the case experimentally, you find this exponent 1. I could come back on this, but The point is that everything seems to be consistent. So since the PDF will be on the, on the network, you can look at the references. Okay, any questions? This is the comparison with experiment. We have many more, you know, for the 10% doping and so on, but I don't want to bore you with this. Yes, Henri?
I assume that all the correlation lengths are coplanar.
Yes, all the correlation lengths are planar correlation lengths.
When you get third.
Yeah, when the third dimension comes in. Yes, Antoine?
To understand this criterion psi versus psi kernel,
Yes.
a simple calculation of the bubble in which I put chi and
Yes,
E,
yes.
maybe that's what you're meant to explain.
Yes, I'm going to explain in the second half. Yeah. But roughly speaking, the phase space is important in this calculation. In high dimensions, you wouldn't see it. Why? Because in high dimension, this line is a true phase transition, and the gap is 0 at this phase transition. So you come in above the gap, and so there's no precursor. But in 2 dimensions, there is a precursor to the real transition, which is here.
The gap you are talking about
Is the antiferromagnetic. So the antiferromagnetic in 3 dimensions, when you get to the transition, there's no the antiferromagnetic gap is 0. It opens up at the phase transition, so there's no precursor region. Yes, Catherine?
Maybe also a question for Henri. Is there the normal state resistivity linear in temperature in electron dope or not?
In the electron dope, it eventually goes to T square, but at high temperature, there's some linear before it saturates. I showed the resistivity curve in the first talk. I can show you later.
The linear regime is in a regime where the resistivity is larger than the ones of a regular value?
No.
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 Smaller.
Yeah. So, well, I mean, it's always, these are always defined within 2 pi, which is almost 10.
Yeah, sure.
So, but at least you see that there's a tendency.
So the regime where it becomes T square, is it big, small,
Oh, it depends on the doping. So if it's very much doped, then the regime can be relatively large. Yeah. But if you are exactly at the quantum critical point, then it's linear all the way to 0 temperature. But it's in a regime where it's quite disordered, then there are other reasons why it doesn't go to T square.
Does the slope depend on disorder?
I don't know. Yeah, you asked me this question. It needs to be.
It's crucial.
Yeah, I know it's an important question.
If
Yeah.
it does,
You need to ask. Yes, you need to ask. I think it is just the usual QCP, but we need to check what you just said.
Then it's not usual QCP.
Right. So, okay, before I show the benchmark, I still show the equations because they are very simple. I want to.
Sorry, who has done these experiments on resistivity?
It was Fournier when he was at Maryland in 1998. They showed this linear thing. I don't know if it has been redone.
It's not been redone?
I don't know.
Well, there's probably work in the group of Rick Brain.
They may have done more, yes. Yes, actually, yeah, because they looked at this quantum critical point. So, yeah, perhaps in the green there is. Yeah.
There's a nice review article.
Yes. Yeah. So I want to just to show that it's much simpler than functional RG or anything. So this is the expression for the spin susceptibility. So you see it's RPA, but you have U spin instead of the bare U. A little bit like in Fermi liquid theory. If you want, the U is not the bare U when you compute susceptibilities. Now, if you look at the charge, it has the same structure, but now you have a U charge. So what we say now is to find U spin and U charge, we just enforce these sum rules. So if I integrate over all wave vector and sum over all frequencies, the spin-spin correlation function becomes equal time spin-spin correlation function. Okay, so it just becomes SZ square. Now if I do this SZ square, I get N up square plus N down square, but N up square is N up because of Pauli principle. So N up square plus N down square is just N. It's the number of electrons. So this is fixed by the Pauli principle. And then we get the cross term, which is -2 and up and down. Here it's +2 and up and down, and that's just subtracting the disconnected piece. So if we were lucky enough to know what double occupancy was, you see we could determine U spin and U charge from these equations. Well, I will show you in the next lecture that we can indeed find an extra equation, and that double occupancy is related to U spin in this way. So if you were to do R3-Fock, then double occupancy would be just n up times n down. But here it is not, in fact. It's determined by U spin, which itself comes from this. So there's a self-consistency relation for U spin, U down. And that's also the physics of Kanamori and Bruckner in condensed matter in nuclear physics, that the bare U is renormalized by summing the whole Born series. So that's the physics that's behind this. Or if you want, when U is large, there's an advantage of having some cusp in the two-body function, because then U can go up and the electrons don't mind because they have zero probability of being there, or very small probability. That costs kinetic energy, but that's limited by the bandwidth. So here are the benchmark comparisons with quantum Monte Carlo. So there's a lot of things, but I mean, we will focus on just a few important ones. So we look at relatively large temperature, but the cluster size are large enough that we can check that there's no finite size effect. So here is the spin structure. Let's focus on the two bottom panels. This is for U equals 4T, so half the bandwidth. And this is the charge structure factor. So structure factor means just that it is spin at Q times spin at -Q equal time. So we move along this trajectory in the Brillouin zone, and you see that the spin fluctuations are larger than the charge fluctuation. You have to look at the scale. So it's a non-perturbative regime. And the TPSC calculations are the solid lines, and the Monte Carlo are the dots. So you see they really fall on each other, and it's not trivial, because here, if you look at the charge fluctuations, you see this is 26% filling. I cannot read. 60% filling, and 94%, so it goes down. It goes up and down. It's not monotonic. And this you can assign to the Pauli principle. In other words, the spin fluctuations are going up, and the charge needs to go down to satisfy some rules. So let's look at something a little stricter. So you look at half filling, n equals 1. This is against the structure factor, but at pi, that's the one that is going to diverge, and that's as a function of temperature. If I was doing RPA, I would get a mean field transition temperature here at 0.75 roughly, in units of hopping all the time. Instead, you see what I get in TPSC is this solid line here. So it starts to go up at a much smaller temperature. So that's the Kanamori-Bruckner effect. You go from an effective U at high temperature that's 4 to an effective U at high temperature that's about 2. But there's something more. Something more is that it does not diverge here. It goes up very quickly. It goes up exponentially, which I will show analytically in the next talk. But so it satisfies Merman-Wagner. And what does the Monte Carlo tell you? Well, a 4x4 system is this. 6x6 it saturates here. 8x8 saturates here. 10x10 saturates here. And there's even a 12x12 site here. So it's not perfect, but you see that the physics is correctly there. Double occupancy is a very important quantity in this approach, and if you plot double occupancy as a function of filling, for U equals 1, 2, 4, so 1, 2, 4 at half filling, it's beta equals 6, but you see that, again, the quantum Monte Carlo points fall directly on the TPSC. And if we had done R3-Fock factorization, then this would be independent of U, and there's clearly a dependence on U. This is comparison with DCA. So we are comparing now a method that's good at strong coupling with a method that's good at weak coupling. And at U equals 4, The DCA calculations are these open, are the symbols, and TPSC is the symbols, the crosses with the line.
Only one should emphasize that since this is a relatively small u, when the collision length is large, one needs to go to large clusters to get these good results.
Yes, you see it was 6436. Now, what about single particle properties? Well, what we have calculated with TPSC now is the spin and charge fluctuations, and U spin and U charge are these irreducible vertices here. Now, if you look at the exact expression for the self-energy, it involves the same blocks. So what we do is use these same blocks to compute the self-energy. The reasoning is that if you look at the collective modes, the details of the quasi-particles are not that important in the sense that collective modes are very much determined by conservation laws. But if you look at the self-energy, then the effect of the collective modes on them is very important because the collective modes go all the way to zero frequency. So the expression that we have in the end is the one that is written there. And you see there's one U is bare, the other one is, if you exchange a spin fluctuation, it's U spin. If you exchange a charge fluctuation, it's U charge. So what is the benchmark? Okay, this is the Monte Carlo calculation at a filling for beta equals 5, U equals 4, and for, I think it's 8x8 system. So you are moving like this in the Brillouin zone. And this is the single particle spectral weight, what you would measure by RPS. And this bump here is for this wave vector at 0. And then you move for different wave vectors. Eventually, you reach the antiferromagnetic zone boundary. You see a pseudo gap opening up. And then if you go far, then the peak just broadens. And you see that the agreement is quite detailed. This is what we get with TPSC here. We get these two bumps, and with the Monte Carlo, we get these two bumps. And the pseudo gap itself, the width, the size is fine, but this is sharper in TPSC than in the Monte Carlo. If you do fluctuation exchange approximation, you miss the pseudo gap. This is for the attractive Hubbard model. I don't show how to do this, but you have to generalize these ideas. And the solid line is the quantum Monte Carlo, and the dashed line is the TPSC. Okay, so I'm going to finish with superconductivity. Are there some questions? Okay, so superconductivity, remember we had this cartoon picture of making a superconductor at weak coupling. It was exchanging antiferromagnetic spin fluctuations. So you can do that with the functional renormalization group also. And what are the results of TPSC? So I show you the benchmarks. This is the D-wave spin superconducting susceptibility. So it's in the particle-particle channel as a function of doping. This is for U equals 4, and the system size is not large, but it turns out that these are very high temperature and there's no size dependence. Beta equals 1, 2, 3, 4. And you see the TPSC is the solid line, and the quantum Monte Carlo are the symbols. So this is pretty trivial here, but you see for beta equals 4, you start to see some dome that is not there if you don't include correctly the antiferromagnetic fluctuation. I will comment on this later, but this has held the field for many years because people said, okay, this is all we can do with quantum Monte Carlo because of the sign problem. And look at the pairing susceptibility. This is for U equals 4, and U equals 0 at beta equals 4 is larger than what we get at finite U. So we're in bad shape. So I will explain how to get away from this. So we cannot do quantum Monte Carlo at lower temperature, but we can do TPSC. And then what we get at U equals 4 is this dome for TC as a function of doping. And the reason it goes down is because of the pseudo gap that's opening up. Now, I showed calculations from DCA that did many different system size and showed that there was a transition. I said it's the best calculation to show the transition. This is this 2005 paper from Jarrell's group. So they did the calculation at 10%, and they found TC is 0.023, which is in this region here of the red, and we have 0.029. So given that it's such a different calculation, it's not so bad. How does it compare with functional renormalization group? This is the right. We have to look to the right here. So this is a TC. This is the dominant fluctuation. This is when they lose control of the functional RG calculation, and that's as a function of T prime over T. So they change T prime, that moves the location of the Van Hove singularity, and they just choose the filling in such a way that they are right at the Van Hove singularity. So then they find that for small T prime, it's dominated by antiferromagnetism, then D wave, then ferromagnetism. And if you look at the same value of U equals 3 in TPSC, you get the same thing, antiferromagnetism, D wave, and ferromagnetism, but in a much cheaper way. So what is the physics of superconductivity in...
Before you go...
Yeah.
On the slide before, yeah, the antiferrotic QCP, where would it be?
Okay, I will. It is somewhere here, just before you get to this tail here. So I will show you. I will comment on this a little bit later. So, what is the physics of superconductivity? In this case, it's really exchange of antiferromagnetic fluctuation. So, if for fun you just take a filling, and then you change T prime. At T prime equals 0. This is the Fermi surface. It's perfectly nested. T prime equals minus 0.3. You get this famous Fermi surface for the cuprates. And what you find is that the dominant instability is x squared minus y squared. If you keep increasing T prime, then the topology of the Fermi surface changes. And now this becomes the nesting vector, and you find that dxy is important. So contrary to BCS, where the density of states play an important role, here it's more than nesting that's important. Now, when you have a T prime, yes. When T prime is big enough, that's what happens. But the T prime is huge. It has nothing to do with... It's just to show this physics of... Okay, now, so TC depends on T prime. So we are at a filling, and take a value of U. For example, U equals 6 is the green curve. And you see that the TC as a function of T prime has this dome shape. So there's an optimal frustration. That's the concept we want to introduce. So if you are too close to a filling, the pseudo gap comes in and kills the superconductivity. If you're too far, there are not enough antiferromagnetic fluctuations. And then you may ask, like Catherine did, where is the antiferromagnetic quantum critical point? We have not located it precisely here, but I just know that there's a region here where we are not in the renormalized classical regime. In other words, the antiferromagnetic correlation length is less than the thermal de Broglie wavelength. So this is shown by this plot. I plot the log of Xi as a function of 1 over temperature. And for this T prime equals 0.31, so that's far to the right. The thermal wavelength is larger than the antiferromagnetic wavelength. And what we know also is that the antiferromagnetic correlation length at optimal doping is about 10. So this is where I want to break. And after the break, I will again show about 5 minutes of transparencies just to expand a little bit on some of the ideas that I will not have time to look in detail analytically. And then I will do these things on the board with the chalk. So if you're not interested in so much theory, you can just leave. Nobody will see.